Okay, so the final exam is on the 4th, right, 3 to 5 p.m. And so I just want to, so it's a 2-hour exam, longer than the midterms. And it has 6 problems, regular problems, plus 1 bonus problems. And the 6 problems, I think 3 or 4, probably 3 to 4 of them will be related to the last 2 lectures, Laplace transform, apply Laplace transform to solve PDEs and Z transform. And the rest, there are probably two other problems that are related to Fourier transform and the sampling theorem. So these are the key concepts that we talk about in the before midterm 2, the second part of this course. So just to note that we do have problems on Fourier transform. It is very basic, just like computing the Fourier transform of some signals, or applying the basic properties of Fourier transform. So it will be very basic Fourier transform problems. And the sampling theorem will be something similar to what we have in the midterm 2. And then the rest of the problems are related to the last 2 lectures. And again, you can use two-sided reference sheets. You can bring your reference sheets for the midterm 2. And today we will go over, so I draft this final review lecture, which contains maybe 4 or 5 problems, so we can go over them. So for the lecture 10, last time we have 2 slides left. So the last 2 slides are about 2 examples, 2 problems that you need to apply the unilateral Z transform to solve these discrete time LTI systems given some initial conditions. So I will skip this part because in the review lecture we have very similar problems. So after the review lecture, you can use these 2 slides for practice. So this final review covers everything that we need for the final exam, starting from Fourier transform, sampling theorem, and then Laplace and Z transform. So for the Fourier transform, let's go over. Yeah, so this is the definition of the continuous time Fourier transform. And we have, for the Fourier transform, we have these basic properties, right? The time shifting property. So if the signals shifted in time, then the spectrum, the Fourier transform will be, its phase will be shifted by a certain amount. So this is the phase shift in the frequency domain. So this is time shifting property. And for the frequency shifting property, it says that if the signal is modulated in time by a complex exponential signal, then the corresponding Fourier spectrum is a shift in the frequency domain. So we will have a frequency shift in the frequency domain. And the convolution property is convolution in time will lead to a multiplication in the frequency domain. So these are the properties that we will frequently use. And here's an example. We may have seen this in the midterm too. So we are given a Fourier transform a pair of Fourier transforms. So for this two-sided exponential signal, the corresponding Fourier transform is given as follows. Then let's look at this signal first, which is a shifted version, time-shifted version of this exponential signal. So this is essentially replacing t by t minus 1. So the signal is shifted to the right by 1 unit. And then for this one, to calculate the Fourier transform, we can directly apply the time shifting property. So in this case, the time shift is just here using the time shifting property. This t naught equals to 1 due to this time shift. And then applying the time shift property, the resulting Fourier transform is the original transform multiplied by this phase factor, additional phase transition factor. So it's e to the power of negative j omega times your time shift 1. And then this is the resulting spectrum. And the third example is taking the previous signal and further modulated by a cosine signal, cosine for t. So we have seen this a lot of times. So the idea is to decompose the cosine using the inverse Euler's formula into the exponentials. And then for each exponential, we can apply the frequency shifting property. So now the signal is modulated by this pair of complex exponentials. And then for each one, we apply the frequency shifting property. And again, when you apply the frequency shift, you should shift the spectrum that you obtained from the previous one. So you need to shift this entire spectrum by 4 units. So basically, all the omegas here and here in the numerator and denominator, both of these omegas needs to be shifted by the corresponding time unit. So we will have these two frequency shifted spectrums. So this is the final spectrum for this modulated signal. And the second example is it's about a sampling theorem. So we are given a signal xt whose Fourier transform takes such a triangular shape. So it ranges from in the angular frequency domain, it ranges from -50 to 50. And then this magnitude is 1. Okay, so we have this triangular spectrum. And then now we sample this signal at this angular frequency omega s, which is 2 pi over Ts. And we have two questions. The first question is, what is the Nyquist rate, Nyquist sampling rate for this signal? And by definition, we know the Nyquist sampling rate is defined as 2 times the bandwidth. And from this spectrum, we can see that the bandwidth is 50. So 2 times 50 gives us the 100 as the Nyquist rate. So we have to sample beyond this 100 hertz, 100 angular frequency in order to have a perfect recovery of the signal. So this is the Nyquist rate. Now the second part of the problem says that let's assume the signal is sampled at such an angular frequency. So it's 80, the angular frequency is 80. And sketch the spectrum of the sample signal. So from this given sampling frequency, we can see that this omega s is below the Nyquist rate. Therefore, if we sample the signal at such a sampling rate, the corresponding spectrums will have overlap. So this is what we expect And then let's sketch the spectrum of this sample signal. So as we have, we have gone through this many times in the lecture 8. So the idea is that we copy the original spectrum and shift it to different locations by a period of the sampling rate. Okay. So for example, for the zeroth copy, it is essentially the original spectrum, ranges from -50 to 50. And note here that all the magnitudes will be scaled by 1 over the sampling period. And in this case, the sampling period can be inferred from the sampling angular frequency. Okay, so it turns out that the sampling period is pi over 40. So therefore, the magnitude scaling factor in the sample signal is 1 over TS, which is 40 over pi. So basically, when you copy this spectrum, all the magnitudes needs to be scaled by a factor of 40 over pi. So here is 40 over pi instead of 1. But the shape remains the same. It is still a triangular shape. So this is the 0th copy. And then we take this copy and shift it to the left and to the right by a period of 80. Okay, so the period is the sampling rate. So shifting this copy to the right by 80, we have now 50 shift to the right by 80, we have 130. Okay, and then -50 shift to the right by 80 gives us 30. So then this gives us the first copy of the spectrum. And we can see that the first copy and the 0th copy do have some overlap area. So this is the first copy. And we can keep shifting this one to generate the second copy. Okay, when k equals to 2 and 3 and so on. And on the left-hand side, we can shift this centered copy to the left and generate the -1, -2, and so on. Generate all the copies on the left-hand side. So in the end, the spectrum looks like this. So we have a bunch of triangular spectrums that are overlapping with each other. So you need to correctly identify these ending points and starting points. Okay, so it's taking the original spectrum shifted by the unit of the sampling rate, and then within this overlapping area, they will superpose these two spectrums. They will superpose. So after the superposition, the resulting spectrum may look like the purple curve. Okay, so we have small area where the spectrum is undistorted, and in these areas, the spectrum will be distorted. So once they superpose with each other, it may look like a straight line. Okay. So in the exam, you need to sketch the spectrum like this, okay, as detailed as possible. Okay, so this is the Fourier transform and the sampling theorem. So it's about the concepts that we talked about in the midterm 2. And then for the final exam, the majority part of the exam will be relating to the Laplace transform and Z transform. So let's go over some examples. So this is the definition of Laplace transform, okay, copied from the slides. And here S is any complex number. So again, I put this ROC in front of everything. So this is the most important thing that you need to pay attention to when you solve these Laplace problems. It's the region of convergence. Always remember, if you miss the region of convergence, So you will only get partial credits. So let's look at one example of how this is calculated. So we are given this signal t times e to the power of 2 times t times u negative t. So this is a left-sided signal because of this u negative t. Okay. And then, well, we want to calculate the Laplace transform and the region of convergence. So following the definition of the Laplace transform, so this is the definition. It's a signal integration the signal times this exponential factor. And then because of this u negative t, right, the u negative t is defined as 0 when t is positive and 1 when t is less than or equal to 0. So basically, this u negative t will restrict the integration to be from negative infinity up to 0. Okay, so we can absorb this u negative t into the limits of this integration. So now we have integration from negative infinity to 0. And then for the rest of the terms, we can combine these two exponentials. So they will give us this factor, e to the power of 2 minus s times t. And then here we can utilize the existing result for integration. So this is a formula for integration. So for any a, integration t times e to the power of at equals to this one. Okay. So in this case, we can just treat a as 2 minus s and then apply this formula. Now doing that, we obtain this result. Okay. This is the integration result, and we need to reevaluate this term at 0 and negative infinity. Now, when we plug in s equal to 0, you can get the result is uh, 2 minus s. Oh, sorry. I think here, okay, it's over t. Yeah. So when you plug in t equals to 0, okay, when you plug in t equals to 0, you get this is 1. So it's, and inside here is 0 minus 1. So you have negative 1 in the parentheses. So overall, it gives us negative 1 over 2 minus s to the power of 2. So this gives the first term. And then we need to subtract the term evaluated at t equals to negative infinity. So you plug in this t equals to negative infinity into this term. This is what you get. And we can see that there are many terms whose values are not determined. And this is where we need to discuss the region of convergence. So especially these two terms involves negative infinity. So if we distribute this exponential term into these parentheses, we have these two terms. So this one multiplied by this one gives the first term, and then this exponential term multiplied by negative 1 will give this term. So in order for both of these terms to converge, we need to discuss their conditions. Now for the second, let's look at the second term first. The second term is what we have seen in the lecture notes. Is e to the power of a complex number multiplied by infinity. And we know that this term converges to 0 only if the real part of this complex number coefficient is negative. So this gives us the condition under which the second term converges. Okay. So this gives us part of the region of convergence. So it's the real part of s minus 2 must be negative. So this is for the second term to converge. But for the first term, it's a little bit different. It takes the form of e to the power of, now it's a complex number times infinity. And then we further multiply this factor by the same complex number times infinity. Okay. So for this one, the ROC is a little bit different because we know because we know that for this is in the form of e to the power of t times t. If you view s minus 2 times infinity as a entire variable. Now such a limit converges as t goes to infinity. So let me write it here. So for this one, first of all, we know that limit e negative t times t as t goes to infinity is 0. Okay, this is an independent result. This is because if you write it in this way, it's limit t over e to the power of t as t goes to infinity. And you can see as t goes to infinity, the denominator explodes exponentially fast, but the numerator explodes only linearly. So clearly the denominator is much, much bigger. So that's why this term goes to 0. And therefore, in order for the second term to converge, here we just need to so this one is e to the power of, let me see these ones. It's e to the power of t times t as t goes to infinity. So I think here, so first of all, we still need this one to converge. It's a little bit misleading here. Let me think about what happened here. This.
When we're doing the ROC, are we supposed to look at the exponential function or the Laplace transform?
So we are calculating the Laplace transform of this signal following the definition, right?
Yeah.
And then now, where does the ROC issue comes from? It comes from when we are evaluating this integration at these limits. For some of the terms, their values are not determined. It may diverge, may or may not diverge. So for these terms, they will impose the conditions. We need to impose some conditions in order for them to converge. And those conditions are the region of convergence. But for example, okay. Yeah, for example, here if you multiply this exponential into this parenthesis, into these two terms, you end up with these two terms. And for the second term is basically this exponential multiplied by 1. For this one, its region of convergence is clear. From the slides, we have a formula that says that this exponential goes to 0 as long as this coefficient, the real part of the coefficient, is negative. So that gives us the first part of the ROC. But in order for, we still need the other term to converge. So the other term is basically this exponential multiplied by this number. And so here it is negative infinity. So when they are multiplied together, we actually have so let me rewrite it in this way. Here is negative infinity, so it's multiplied. Here we have negative sign, so they can cancel out. So what we have is e to the power of 2 minus s times negative infinity. So it's negative infinity. Now times 2 minus s times infinity. Right. So for this part, it's the same. I simply move the negative sign in the front. And for this one, the negative infinity cancels with this negative sign. So I can just look at 2 minus s times infinity. Now this is, if you view this as t, this is exactly e negative t times t. Therefore, based on this limited result, this term as t goes to infinity, but because now t is going to infinity, as t goes to infinity, this term automatically converges to 0. So all we need to make sure is that this t goes to positive infinity. Goes to positive infinity. But this is t divided by e to the power of t. If t goes to positive infinity, this term goes to 0, right? Because the denominator explodes exponentially fast. But if t goes to negative infinity, this term will diverge, right? Because the denominator converges to 0 and the numerator goes to negative infinity. So the only way to make this term converge is to make t goes to positive infinity. And in order for that, in order for the t to go to positive infinity, we must have this coefficient must be positive. Yeah, this coefficient must be positive. So that gives us RE2 minus S must be positive. This is the second condition. So we have two ROC conditions. One is from this term, where we derive that the real part of S minus 2 to be negative. This actually means the real part of S must be less than 2. Now, for the second term, we derive that the real part of 2 minus S must be positive. And this also shows that this also equals that RES less than 2. If you move RES, so it's 2 minus RES greater than 0. So these two conditions, they are the same, essentially. They are the same. So in the end, this is the overall ROC. This is the overall region of convergence. And within this region of convergence, both of these terms will converge to 0. Okay. This term converges to 0 and this term converges to 0. So in the end, the entire second term converges to 0 within the ROC. So then the conclusion is that Okay, within this ROC, the Laplace transform equals to this one. The second term basically converges to 0 within the ROC. So in the end, you simplify this a little bit. So this is the final Laplace transform, and this is a final region of convergence. Okay, so this is the first approach where we follow the definition of Laplace transform and to calculate its Laplace transform and the region of convergence. So in this calculation, you need to pay attention to these limits. It is these terms will lead us to the region of convergence. And this is approach one. Now for this example, we have another approach. So basically, if you look at the signal, so in the class we have derived the Laplace transform for this type of signal, for an exponential signal multiplied by a unit step type signal. But this xt is, we can view it as t times such a signal. So suppose we are from the existing Laplace transform table, suppose we already know the Laplace transform of this one, then the signal xt is essentially multiplying the signal by t. And this additional factor t can be introduced by one of the properties of Laplace transform. Now, specifically, we can use the differentiation in the S domain property to introduce this factor. Okay. So now let's look at how to introduce this factor by leveraging the differentiation in the frequency domain property. So from the table, we are given such a pair of Laplace transform. This is given in the slides. Here we need to because the signal has u negative t, so we need to look at the second example. Right, the second example is negative e to the power of negative at times u negative t. For such a left-sided exponential signal, the Laplace transform is given by 1 over s plus a with such a region of convergence. So this is given. And then comparing this example with our signal, we can see that it is very similar to this part of the signal. Well, we can take a to be -2, right, so that we can recover that signal. And this negative sign is just a linear scaling of the magnitude, and we can handle that. So what is important here is to introduce this t factor, okay, by leveraging the differentiation in time in the S domain property. So the differentiation in the S domain property says that such a signal takes such a Laplace transform. Okay, so if yt has a Laplace transform ys, then negative t yt has a Laplace transform dys ds. So it's the derivative of in the S domain. And by leveraging this property, we can introduce this t factor or this negative t factor in the signal domain. So that's how we get this coefficient. Okay, now here's how we apply this one. First of all, I define this signal as yt with a equals to -2. As we discussed previously, when we set a to be -2, this part of the signal right, equals this part of the signal of interest. So we define yt we define yt in this way by setting a to be -2. And then this table tells us that yt has such a Laplace transform with such a region of convergence. Right? You simply plug in a equals to -2. Okay. So this is the Laplace transform for yt. Now you want to apply this differentiation in S property on to yt. So this property says that -t times yt, but -t times yt, but now yt is defined in this way. So it's -t times this yt signal. This corresponding Laplace transform is the derivative of your original Laplace transform. So by applying this property, we know that, okay, the Laplace transform is given in this way, with the same ROC. Now this derivative is very easy to evaluate. And then you can see now by leveraging this property, the signal that we are looking at is exactly our signal of interest, right? Because -t, this negative sign cancels with this negative sign. So we end up with the signal of interest. Okay. So the idea is to view this signal as an existing signal, a signal that we are familiar with, multiplied by this t factor. And then this t factor can be introduced by using the differentiation property of the Laplace transform. So when you apply these special properties, make sure you have everything well defined or clearly defined, because we can see that here there's a lot of negative signs that sometimes it makes a little bit confusing. So you need to clearly define, okay, what is your original signal yt? Here we define yt in this way. Okay, because I know we can see from the differentiation property, it introduces a factor of -t. But there's no negative sign in the signal of interest. Therefore, I need to define yt with an additional negative sign so that in the end they can cancel out. So this is my yt. And then for this yt, its Laplace transforms can be directly obtained from the existing table. And once we figure out yt, applying this property is very straightforward. Okay. So taking differentiation, this gives us probably -1 over s minus 2 to the power of 2 with the same region of convergence. Okay. So for this example, we have two different approaches. You can choose any one, but normally the second one is more effective. It avoids the discussion of region of convergence. Okay, so any questions? Yeah, so the final exam will be something similar to this. So most likely you will utilize the properties of Laplace transform to simplify your calculation. And then let's look at some examples where we apply Laplace transform to solve partial differential equations. So here we have a partial differential equation defined in this way. Okay. This is the second order derivative of yt. Now the first question is to find the system in response, hs. And this is similar to what we did in the Fourier transform. We simply take Laplace transform on both sides. And then the system response is given by capital Y over capital X. Now, taking Laplace transform on the left-hand side, the second order derivative of yt after taking Laplace transform. So by the differentiation property of Laplace transform, we know that this gives us s squared times ys. And for the first order derivative, we get this one. And this is 6yt, we get 6 times ys. Okay. On the right-hand side, we get xs. So this is the system equation in the s domain. And then from here, we can solve for y over x. So this is capital H. And you can get 1 over s squared minus s minus 6, which can be further decomposed into two fraction numbers using partial fraction expansion. So here I skip the steps. So this is the system response. And the second one is, the second problem is to identify the zeros and the poles of this system response. From here, we can see that it is in a rational form. Okay. And for the regular zeros and the poles, we can see that it has no regular zeros because the numerator is 1. For the regular poles, we have 2 roots of the denominator. So we have 2 regular poles, 3 and -2. And in addition to that, we need to further consider infinity. And because the order of the denominator is bigger than the order of the numerator, so as s goes to infinity, the entire number will goes to 0. So infinity is 0 in this case. Okay. So we have 1, 0, infinity, which is infinity, and 2 poles. And then another small question is that what is the region of convergence in order for the system to be causal? Now, so let's go back to the causal part, right? We know that causal systems means that the system response, impulse response, is a causal signal. So HT is right-sided. And from the properties of causal systems, we know that the region of convergence of a causal system must be to the right of the rightmost pole. Okay. When the system response takes a rational form. So in this case, we have 2 poles. One is -2 on the left-hand side of the y-axis. One is 3. So the ROC for a causal system is to the right of the rightmost pole. So in this case, is RES greater than 3. Okay, so in this case, the rightmost pole is 3. Right? Because infinity is a 0, it's not a pole. So this is the region of convergence for a causal system. And the third question is continuing this one. Now, given such a causal system, is it stable? So check the stability of the system. And for Laplace transform, we know that stability means the ROC must include the y-axis. Right? ROC must include the y-axis, the j omega imaginary axis. Now, in this case, we can see that this ROC does not include the y-axis because 3 is to the right of the y-axis. So it is not a stable system. So if you want it to be causal, it cannot be stable for this example. Okay. And the last one is to find out the corresponding system impulse response given this frequency response and given this ROC. Now this part is standard finding out the inverse of the given Laplace transform. So you can apparently we can refer to the existing tables. For this one, so what we are given is that we are given this now suppose K1 and K2 are some constants. So this is the overall ROC for both terms, which is the intersection of their individual ROCs. So from here, we need to go back and figure out their individual ROCs. And then we can refer to the table to find the inverse. And because now we have two poles, one is -2, one is 3. And ROC is to the right of 3. So clearly for the second term, the ROC is just because 3 is already the pole of this term. So the corresponding ROC is just the given ROC. And for the first term, the ROC is either to the left of -2 or to the right of -2, right? Because of this pole, -2. But if the ROC is to the left of -2, then the overall ROC can never be to the right of 3. So that leads to a contradiction. So the only possible ROC for this one is bigger than -2. And then these two ROCs taking the section indeed gives us this overall ROC. So these are the corresponding ROCs for both terms. And then given this, you look into the table, you can figure out the inverse. Okay. So in this case, both of these two parts corresponds to right-sided signals. So there must be a UT in your final answer, because the ROC are both of the ROC are right-sided. Okay. So here, so for this one, we apply Laplace transform to analyze this LTI system, and then from the Laplace transform, we can discuss the corresponding ROCs of causal systems or stable systems. And then from there, we can identify the corresponding impulse response of the system. And the last example is very similar to the, oh, okay. So the last part is about Z transform. And here, here's the original definition of Z transform. And in addition to the Z transform, we also define the unilateral Z transform, okay, which is starting from 0 to infinity. And these are the properties. So here I only listed the properties of the unilateral Z transform. Okay. The properties for Z transform can be found in the slides. But we will use these properties to solve the follow-up problem. So the most important property here is the time shifting property, because we need to apply unilateral transform to solve the difference equations. So if a signal is shifted in time by 1, like xn minus 1, then the corresponding unilateral Z transform is given as follows. So it's x negative 1 plus Z inverse times xz. Okay, so there's a dependence on the initial condition. And then for xn minus 2, this is the unilateral Z transform. It depends on these two initial conditions. So here is an example, like given this difference equation with these initial conditions, find out there are several parts. Let's go over them one by one. The first question is find out the unilateral Z transform, YZ. And then you just take unilateral Z transform on both sides. Okay, Yn gives Yz. This is the unilateral transform. Now Yn minus 1, we need to apply this unilateral transform, time shifting property. So this gives us y negative 1 plus this part. Okay, this is according to the first time shifting property. And for this one, because it's shifted by 2, Yn minus 2 shifted by 2. So we need to apply the second property, which gives us 3 terms. And these 2 depends on the initial conditions. On the right-hand side, we have xn, and the unilateral Z transforms xz. Now we just plug in all the initial conditions into this equation. So y negative 1, y negative 2, they are given. So plug in these ones. And this, on the right-hand side, xn, the input signal is given as 0. So we have 0 input to the system. So because the input is 0, so the corresponding unilateral transform is also 0. Okay, so we, on the right-hand side, we just have 0. Now you plug in all these initial conditions, we get this equation, and then you can solve for YZ. Okay, solve for YZ. In the end, YZ is given as this one. And you can decompose, you can factorize the denominator into these 2 factors. And then you do a standard partial fraction expansion, you get this 2 fraction numbers. Okay, so this is the unilateral Z transform for this system. And the second question, I think, is to find out the inverse corresponding to this unilateral Z transform. So as we discussed before, for the unilateral transform, we don't need to explicitly know the region of convergence, right? The ROC can be inferred from the unilateral Z transform. The idea is that for unilateral Z transforms, the ROC is always outward a certain area. So it's always towards infinity. So it's not inward, it's always outward. It's like for the unilateral Laplace transform, the ROC is always right-sided. Here, for the the unilateral Z transform, ROC is always outward. So here we can, from the unilateral transform, we can see 2 poles. One is 2, one is negative 2, one is 3. We have 2 poles on the denominator. So we can draw them here, negative 2, 3. These are 2 poles. And because it's a unilateral Z transform, so by the property of a unilateral Z transform, the ROC is outward. And at the same time, the ROC should not contain any poles. So the only possibility is outward the outermost pole, which is 3. Therefore, the ROC is just the region. You draw a circle as with a radius 3, and ROC is outward this circle. Okay, so now you have this overall ROC. And then you can go back, figure out the individual ROCs for these two parts. And clearly, this ROC is an ROC for the second part because the pole is 3. And for the first part, the pole is -2. So the only possible ROC is Z greater than 2. So that is for the first part. It is also an outward ROC. And then given these individual ROCs, you can leverage the existing table of Z transform to find out the inverse. So in this case, both ROCs are outwards. So the inverse should be corresponding to a right-sided signal. Okay, so this is about the unilateral Z transform. And then you can go back to the slides. We'll go back to the last 2 slides of the lecture 10, which are very similar, very similar examples. We have difference equation, and we have initial condition and the given input. So you can completely solve this difference equation, okay, following the same logic. So here this is a first order difference equation. So we are only given one initial condition, and the input is not 0. So it is given as a unit step function. So you can calculate. So instead of having 0 on the right-hand side, right here we are having a 0 input. So instead of having 0 here, you should calculate the unilateral Z transform of this given input. And I think this for this one, it is already given in the lecture slides. And the last slide is another example on on a second order difference equation. Okay. And we are given 0 input and 2 initial conditions. So you can follow the same idea, solve this unilateral, apply the unilateral transform, solve this equation for the unilateral transform. And then from there, you can directly identify the inverse. So you can, in the end, you can figure out the output signal of this system. So this is the unilateral Z transform. And I think for the unilateral Laplace transform, it's the same idea. You can refer to the slides, lecture 9. You can refer to the examples given in lecture 9. But we have many examples at the end of this lecture. Yeah. So how to leverage unilateral Laplace transform to solve the partial differential equations. Given some initial conditions. Yeah. So something like this one. Given a PDE system and even the input signal and some initial conditions, we want to solve this equation and figure out the output signal. So you apply the unilateral Laplace transform, which involves these initial conditions. And then in the end, you figure out the unilateral Laplace transform. And from here, you can directly identify the region of convergence because the ROC is always right-sided. So here, it should be to the right of the rightmost pole. Now, in this example, the rightmost pole is 0, so its ROC is to the right of 0. With this ROC, you can solve this, solve for the inverse of this Laplace transform. Right. So I think this is everything I have for the final exam. So it will be somewhat similar to the problems that we discussed here. So I think you can go over this review lecture. It is in the, you can find it on this page, on the Canvas page. And it's 2 hours for 7 problems. So I think most of all the problems are very standard. If you follow this standard logic. Okay. So it's basically reviewing this review lecture and maybe reviewing this lecture notes 9 and 10. And for the homework, you should also review the homework problems. And this should be sufficient for the final exam. Okay, I think it's almost 1:30. So we have 15 minutes left. If you have if you have any questions. Okay, thanks. And so if you have, do you have any other questions?
I was wondering if we could go over the
Okay.
second to last problem on the last homework. It was like homework 10, I think.
Okay. Yeah, we can do that. But there are some other questions. Let me. So what is your question?
We review discrete time Fourier transforms as well, or
Okay.
similar to
I think I don't remember if I have one relation, but if we have it will be based on the basic definition, calculating the DTFT of a given signal. It will be the very basic one. Yeah. Which one will? Yeah, we can look at this. Let's start with homework 9 first. So which one? Okay, finding the poles of the last problem. So for the poles, it's basically the solution of this equation, right? For the root of the denominator, right? So it is, for this one, we don't have real roots, so it's a complex number. So it's a pair of 2 complex numbers. You can apply there's a formula for second order equation, right? You apply that formula, you can get a pair of 2 roots. So it should be 2 complex numbers on a vertical line. Okay, so you just look for the formula for second order equations. Okay.
Can we do the inverse for that too?
The inverse for this one.
Yeah.
So I will, okay, I think the idea is to, because this one is very special in the denominator, in the numerator, it has the exponential part. So, so this is not a rational Laplace transform. So I think what you do is you can decompose this one into two parts. One is s, one is e to the power of negative s. So if you do that, okay, so you decompose, you separate these two parts, and now if you have the ROC, now for the first one, it should be straightforward. Once you have you have the poles, you have the ROC, you can find the inverse. You do a partial fraction expansion, right? This is standard. Now for the second one, you need to handle this exponential. And the hint is to use linearity and time shifting property. Well, the linearity is to decompose, to separate these two parts due to the linearity of the transform. And then we can for this exponential part, we can think of the time shifting property. So we know time shift will lead to such a frequency shift, a phase shift in the S domain. So you can view this as 1 over this one times e to the negative s. Well, this is caused by a time shifting property. So what you do is to first find out the inverse for this one, and then this one is just due to a time shift. So you just shift the signal corresponding to this one by 1 unit. Is this clear?
Yeah, that makes sense. Thank you.
I mean, there are some details, but the logic is, the basic logic is this one. Okay, you apply the time shifting. Otherwise, for this one, you cannot, we don't have a formula for this type of inverse Laplace transforms, right? It has an exponential part, but we can address it by the time shifting property. So for this one, we can find the inverse. You do a partial fraction expansion, you have the ROC, you can find the inverse signal. And then this one says that you need to shift the signal to the right or to the left by 1. Okay, so what is the other question for homework 10?
Yeah, it was part D of 10.22.
This one?
No.
Okay,
Yeah, 10.22 right there.
well, okay. Determine the Z transform for the voice sequences, sketch the pole 0 plot. I'll say, okay, so it's basically calculating Z transform. For this one, Well, so what is your do you have any idea on this one? The last one, right?
Yeah, that's the one I'm looking at.
Is a exponential times cosine times u negative n minus 1. So I think again, okay. So we can just rewrite it in this way. It's 4 times n 4n cosine something, okay, 2 pi. I don't know why they write 2 over 6. So it's just pi over 3n plus pi over 4 u negative n minus 1. I think you can, this can be understood as modulation, right? So it's so as long as you can handle this Z transform, then you apply that modulation property or this frequency shifting property of the Z transform to handle the cosine part. But the first question is what is the Z transform of this one? And I think you can. This is related to the existing example, to the table, because this is exponential form, exponential times a u function. So what you can do to relate this one, to rewrite this one into that exponential form. So you can do a change of variable. So it's 4 equals to e to the power of log 4, right? Log 4 times n. So it's e to the power of n times log 4. This is 4 to the power of n. And right, and then this is very familiar. This falls into that example is e to the power of alpha n times un or u negative n. But well, this alpha is basically, yeah, where this alpha is basically log 4, and then you can apply the existing table of Z transforms to get the Z transform of this one. Once you have that, you go back to introduce this additional cosine. Now this cosine is by the inverse by the inverse Euler's formula. It's EJ okay plus E negative J, same thing, divided by 2. And then for each exponential part, for example, for this one will be multiplied by this one, right? So then, and then you can apply the frequency shifting property. So, but before that, you notice that there's a constant phase shift in this one. So you can decompose it into 2 parts. One is the constant part. One is the frequency shifting part. Right. So this is just a universal constant. So this one will be multiplied with the signal. It's kind of like a constant scaling of the magnitude. And then this one, when you multiply with the signal, you can apply the frequency shifting property. And you do this for both parts. You do this for both parts. Okay, is this clear?
Sort of. I got to the EJ, like I have this over 2. I understand what you're doing there. How do
Okay.
you separate the What happened to the other or the real part?
Well, when you multiply this one, right, with the signal, this is the exponential part. So you can rewrite. So this one equals to the product of these two exponentials, right?
Mhm.
And the first exponential part is a constant, is a complex number, fixed complex number. It doesn't depend on n. So this is a constant that you can put this one with your signal, or you can just treat it as a constant scaling factor. You can put it aside. And for the other part, for this one multiply with the signal. For this one, you can apply the frequency shifting property, right? Is the signal modulated by a complex exponential signal?
Okay, I think I get that.
Yeah. So the only difference is that here we have an additional phase shift in the cosine signal. That eventually that only leads to a constant scaling in the magnitude of the signal.
Okay. Do we account for the u of negative n minus 1?
U negative. So that one, as I said, so you first need to identify the the z transform of this signal, right? And the way you identify it is to rewrite it into exponential form. And for this one, we are given that table of z transforms. And one of the examples in the table handles the u negative n minus 1. If you check lecture 10, there's lecture 10. I think, okay, it's this one. Oh, we don't even need that exponential reformulation. Okay, you can just apply that one. You can ignore this. Right. 4 to the power of n u negative n minus 1. This is a to the power of n u negative n minus 1. Right, so you just set a to be 4, and there's a negative sign in front.
Oh, I see. Okay, we did that example. Okay, thank you.
All right. So if there's no other questions, I think you can talk to me afterwards in the office hour, and so I will send the email and confirm the exam date again. So it's on the May the 4th, 3 to 5 p.m. So I will see you. I will see you then.
Thank you.
And remember, there's as I said in the syllabus, if you provide feedback to this course, you can get an additional bonus for the final grade. So yeah, remember to do that. No, there's a course feedback like survey, right? If you yes, in person plus online, I will hold both simultaneously.